If you're watching this right now, chances are you're one of the 4.6 billion people on planet Earth that have access to the internet. And as a regular internet aficionado myself, I'd be willing to wager that you've read an article. These short blocks of text convey to us an unlimited amount of information, they shape our opinions, and they give us the inside scoop on what's really happening in the world around us. But if you've ever ventured to the second page of Google, you might have noticed that not every article gets featured on our feeds and in our phones. And if you've ever written an article yourself, you might have been confused and frustrated as to why it is that your article about how boba shortages are the next pandemic only got 3 claps, when a picture of an egg got 18 million likes. Now I can already hear you guys typing away at the comments, "It's because of the algorithm, Chris, it's because of the algorithm." And you'd be right. The algorithm, or the internet's robotic overlord, controls everything that we see on our screens. From what news notifications we get on our phones, to what research papers come up when we want to learn something. The algorithm is an inescapable part of everyday life. This is especially true right now during a global pandemic when our entire lives are on the internet. Now, I want you to imagine if we, the every person, could somehow control the algorithm. What if we could predict what the algorithm would promote and what it would demote? And I made a code to do just that. Meet Vaughn, the medium success predictor. Vaughn, short for viral or nah, is an algorithm I made that looked over a bunch of articles and it learned what works and what doesn't. It then applies this knowledge onto your article, telling you whether or not it thinks you will go viral. But how does it work? Vaughn works on a supervised machine learning algorithm. And what that basically means is we give Vaughn the answers and we try to let it figure out how we got there. You can think of it sort of like learning how to walk. Instead of giving our toddlers step-by-step instructions of how to calculate where your foot will go and how long your stride has to be, we just let kids watch us walk. After observing for a little while, they'll try it themselves. And if they fall, then they know that's not how we walk. But if they don't fall and they're able to walk, then they'll know this is walking. Vaughn does the exact same thing with articles. Okay, so it makes sense at a super high level, but how do we actually do that? To answer that question, we need to talk about data. Data is the backbone of all machine learning, with about 80% of the time you spend on any project being cleaning the data. For Vaughn, I use a data set from Kaggle, which is sort of like Airbnb for data scientists. And this data set included Medium articles and a bunch of details about them, like the author's name, the claps, the reading time, a link to it, the title, and the text. What I wanted to do though is I wanted to know how we could predict it using just the content of the article. So to do that, I isolated the claps and the article into their own lists. Next, to stop the algorithm from just memorizing the answers, we split up the data into what's called test data and training data. What this means is that it learns all the problems and answers on the testing data, and then we switch everything around and try to test the concepts with the training data. Sort of like how you get a practice test before the actual test. Next, we have to do this thing called preprocessing. And basically, the reason we do that is because computers at their core are just really, really big, really fancy calculators. Everything you see on your screen, from your YouTube videos to your articles, are just a compilation of a bunch of math. So we have to figure out how we're able to turn the words of an article into those numbers so that the computer can do calculations on it. The process of turning words into something that computers can read is called preprocessing. And that starts with a process called tokenization, which is just fancy talk for breaking it up into sections. For Vaughn, I use word size sections. Next, because the and the have the same meaning, we should lowercase everything. And finally, we do this thing called encoding. So basically what encoding does is it sets a number to mean each word. So say we had an example line like this. Each word would have its own number. Then, every other time the algorithm sees those words, it'll change that word out for the number it saw earlier. And then finally, once we have everything in number form, we have to do a process called padding and truncating. We do this to make each input the same size. And we'll talk about why we have to do that later. But padding basically just means adding empty values to the end of something. And truncating just means cutting it off at a certain point. But why do we have to have our data be the same length? We need our data to all be the same length because we need the same number of input nodes on a neural network. And a neural network is sort of like the holy grail of machine learning. They're basically mathematical representations of how our brain learns. And the structure of neural networks basically goes like this. We have 3 types of layers. We have an input layer, which is basically all the data that we have. And this is why we need it to be the same size, because the input layer will have a certain number of nodes or little places to put the data based on how many inputs there are. So if each of the inputs is wildly different, then we'll need a different model for every one, and it doesn't make sense. Each of these nodes or places in the input layer are then multiplied together and then multiplied by a weight or some constant that we can change into a node in the hidden layer. And then finally, after who knows how many hidden layers, we output all of that into one node called the output layer. The output layer will tell us what the algorithm's prediction is. The algorithm learns then by changing the weights, if you remember them. It changes the weights that all the nodes are multiplied together by, and it keeps changing them until it gets the most accurate answer. Now that's great, but what does Von use? Well, for words like articles, people typically use what is called an RNN, or a recurrent neural network. And I won't get into the specifics, but basically the idea is that typical neural networks, like the one I explained earlier, only account for each word at a time. Whereas recurrent neural networks can think of the entire sentence. This is because the in front of, say, the elephant might not have the same meaning as the in WTF, even though they're the same word. For Von specifically, I use what is called an LSTM, or a long short-term memory network. And to understand those, let's look at this cereal box. I want you to read all these words and then look away. Now, if I ask you to recite some of the things that were on the box, you probably get the main idea, even if some of the semantics weren't necessarily accurate. Like oat cereal, crunchy, it's a good way to start today. This is because you were able to pick out the most important words of each sentence and selectively forget the things that didn't matter, like the and get. Traditional RNNs, like the ones we talked about, don't have this ability, so they look at every single word with the same importance. And while that might not sound like a problem, when it does become a problem is when the algorithm starts forgetting important things to remember things like a and the. What LSTMs can do is it can do the same thing we did and selectively forget parts of the sentence so that it can remember the main ideas. So putting it all together, we had data analysis where we split up the data into things that we could use and then turned it into numbers so that our computer could calculate it. Then we use LSTMs to turn these numbers into calculations. Next, we use another hidden layer to turn those calculations from the LSTM into a prediction. And that prediction is Von's prediction. And then judging by how good that prediction is, the computer will automatically adjust some parts or weights of that neural network. This is how most natural language algorithms are structured. But it doesn't work. Well, currently, Von has about a 70 to 80% accuracy, meaning that it's only right about 70 to 80% of the time, like a C. So it's not necessarily the holy grail of predictions that I want it to be. Despite that, I completely invite you to come play around with Von. Enter some of your articles and tell me if it works for you in the comments down below.